Welcome back to Calculus 1. In the previous lesson, we developed the basic idea of a limit and learned how to estimate limits from tables and graphs. In this lesson, we will move from estimating limits to evaluating them analytically. We will use the properties of limits to break complicated expressions into simpler pieces, and we will see why direct substitution works for many familiar functions. We will also learn what to do when substitution produces the indeterminate form 0 over 0, and we will introduce two special trigonometric limits that will be useful throughout calculus. Let's get started. Here's what we will cover in this lesson. First, we will learn how the limit rules allow us to break a complicated limit into simpler pieces. Next, we will use direct substitution to evaluate limits and identify the conditions under which substitution is valid. We will then examine limits that produce 0 over 0. Remember that 0 over 0 is not an answer. It is an indeterminate form telling us that the expression must be rewritten before we can evaluate the limit. Finally, we will introduce two special trigonometric limits. Many limits can be evaluated by direct substitution. When substitution produces an indeterminate form, another method may be needed. We will begin with three basic limits that follow directly from the meaning of a limit. First, the limit of a constant is simply that constant. A constant function never changes, so as x approaches any value, the output remains fixed. Second, the limit of x as x approaches c is c. The output is the input, so the output approaches exactly the same value as x. Third, the limit of a power of x is found by raising c to that same power. The example at the bottom illustrates these ideas. The constant function remains at 5. When x approaches negative 2, x approaches negative 2. And when x approaches 7, x cubed approaches 343. These simple results form the building blocks for the limit of properties on the next slide. Suppose the limit of f is L and the limit of g is k as x approaches c. The limit law tells us that we may perform ordinary algebra on those limiting values. A constant multiple may be carried throughout the limit. For a sum or difference, we take the limit of each function and then add or subtract the results. For a product, we multiply the two limits. For a power, we raise the limit to that power. The quotient rule works in the same way, with one essential restriction. The limit of the denominator cannot be 0. We must never divide by 0. So the general strategy is to take the limit of each piece and then combine the results using the corresponding algebraic operation. These laws provide mathematical justification for direct substitution. Let's apply the limit properties to several examples. In the first example, we substitute 3 for x. The constant multiple and power rule allows us to evaluate the expression directly, giving 45. In the second example, substitute negative 1 for x. The two terms add to 0, so the limit is 0. For the quotient on the right, substitute negative 1 for x in both the numerator and denominator. The denominator becomes negative 2, not 0, so the quotient rule applies and the limit is 2. In the final example, substituting 1 produces negative 5 inside the parentheses. The power rule then gives the result shown on the slide. Direct substitution is not merely a shortcut. It works here because the limit properties make each substitution valid. The limit laws give us a very useful conclusion about polynomials. A polynomial is constructed from constraints and powers of x, using addition, subtraction, and multiplication. Because each of these operations obeys the limit laws, we can evaluate the limit of a polynomial by substituting c for x. For the first example, substitute 2 for x and simplify. The result is 1. A rational function is a quotient of two polynomials. We may also use direct substitution provided the denominator does not become 0. In the second example, substituting 3 gives 10 in the numerator and 2 in the denominator, so the limit is 5. If the denominator becomes 0, the quotient rule does not apply. We must examine the result and choose another method. Direct substitution also works for radicals and trigonometric functions when the point lies in the appropriate domain. For an odd root, the input may approach any real number. For an even root, we must remain within the function's real value domain. In the first radical example, substitute 9 for x, giving 3. In the second, substitute -27 and the cube root is -3. The basic trigonometric functions are also continuous wherever they are defined, so their limits may be found by substitution at those points. For the first trigonometric example, substitute pi for x. Since cosine of pi is -1, the product is negative pi. In the second, tangent of pi over 4 is 1. The key idea remains the same. Substitute, provided the function is defined at the value being approached. A composite function places one function inside another. To evaluate its limit, begin with the inside function. Determine the value that the inside is approaching, and then apply the outside function to that result. In the first example, substitute 3 into the expression inside the cube root. The inside approach is 8, and the cube root of 8 is 2. In the second example, substituting 2 into the expression under the square root gives 4/5. Taking the square root and simplifying gives a value shown on the slide. This works because when the outside function is defined and has no break, at the value produced by the inside function. A useful way to think about this is that the outside function only sees the number the inside function is approaching. Now it's your turn. For each of the 4 limits, try direct substitution and observe what happens. Do not assume that every problem will immediately produce a final answer. Your first goal is simply to identify the result of substitution. If substitution gives a real number, the limit can be evaluated directly. If it produces 0/0, the problem is not finished and the expression will need to be rewritten. Pause the video now, work through all 4 examples, and decide which ones give a number and which ones do not. Then resume the video to check your answers. Let's check your answers. For the first limit, substitute 2 for x. Because the expression is a polynomial, substitution works and the limit is 10. For the second limit, substituting 1 makes both the numerator and denominator 0. Therefore, we obtain the indeterminate form 0/0. This is not the final answer. For the third limit, substitute 0 for x. The expression inside the square root becomes 4, so the limit is 2. For the fourth limit, substituting 4 again makes both the numerator and denominator 0. This problem also requires another step. So problems 1 and 3 are complete. Problems 2 and 4 require repair. 0/0 is a signal to rewrite the expression, not a conclusion about the limit. When direct substitution produces 0/0, we call the result an indeterminate form. The word indeterminate is important. It means that this form alone does not determine the limit. It does not mean that the limit fails to exist. The key fact shown here allows us to repair many of these expressions. If 2 functions agree everywhere near C, except possibly at C itself, then they have the same limit as x approaches C. In this example, factoring the numerator reveals a common factor. After the factor is canceled, the original quotient agrees with x plus 1 everywhere except at x equals to 1. The original function is undefined at 1, while the simplified function equals 2 there. But the limit does not use the values at the point itself. It examines nearby values. Therefore, we may work with the simpler expression when evaluating the limit. This slide presents 2 common algebraic repairs for the indeterminate form 0/0. The first method is factoring and canceling. In the first example, factor the difference of squares in the numerator. The common factor cancels, leaving x plus 1. We can now substitute 1 giving a limit of 2. The second factoring example works similarly. Factor the denominator as a difference of squares. Cancel the common factor and then substitute 4 into the remaining expression. The limit is 1/8. The second repair method is rationalization. Multiply the numerator and denominator by their conjugate. After simplifying, the factor of x cancels and direct substitution gives 1/2. In each case, the repaired expression agrees with the original function at every nearby input, even though it may differ at the single point being approached. That is why the repair preserves the limit. Not every limit can be evaluated through direct substitution or an algebraic repair. Sometimes a function we care about is difficult to analyze directly, but we can trap it between two simpler functions. The squeeze theorem says that if f remains between a lower function and an upper function near C, and both outside functions approach the same number L, then f must also approach L. The graph illustrates the idea. As x moves towards C, the lower and upper functions close in on the same height. Because f is trapped between them, it has nowhere else to go. Notice that the theorem requires both outer functions to approach the same number. If their limits were different, they would not force the middle function toward one particular value. So the squeeze theorem allows us to determine a difficult limit indirectly by controlling the function from above and below. We now come to two special trigonometric limits that are used repeatedly in calculus. The first says that the sine theta divided by theta approaches 1 as theta approaches 0. The second says that 1 minus cosine theta divided by theta approaches 0. Direct substitution gives 0 over 0 in both cases, but ordinary factoring does not repair them. The first result can be established with the squeeze theorem. Near 0, sine theta divided by theta is trapped between cosine theta and 1. Both outside expressions approach 1, so the middle expression must also approach 1. The second special limit follows from the first and has a limit of 0. These results require angles to be measured in radians. If angles were measured in degrees, the first limit would not equal 1. Let's use the first special trigonometric limit in two different forms. In the example on the left, tangent is hiding the sine expression that we need. Rewrite tangent as sine divided by cosine and separate the expression into two factors. The sine factor approaches 1 by the special limit, and the reciprocal of cosine approaches 1 by direct substitution. Their product is therefore 1. In the example on the right, the angle in the numerator is 4, theta, but the denominator is only theta. The special limit requires the same angle in both places. To create the needed form, place 4 theta in the denominator and compensate with a factor of 4 in front. As theta approaches 0, 4 theta also approaches 0. The special limit then gives 1, and the remaining factor produces a final answer of 4. The strategy is to rewrite the expression until you can recognize sine of an angle divided by the same angle. Let's put the main ideas together. Begin with direct substitution. Polynomials, rational functions with non-zero denominators, radicals, trigonometric functions, and appropriate composite functions. Substitute the value being approached and evaluate. Next, read the result carefully. If substitution gives a real number, that number is the limit. If it gives 0 over 0, the expression needs another step. To repair 0 over 0, factor and cancel or rationalize, then substitute into simpler expression. The two special trigonometric limits are foundational results. We recognize and apply them rather than repairing them algebraically. In the next lesson, we will study continuity. We will identify functions that have no breaks and examine what happens at points where a break occurs. Thank you for watching. In this lesson, we use the properties of limits, direct substitution, algebraic repair, and the squeeze theorem, and two special trigonometric limits to evaluate limits analytically. In the next lesson, we will connect these ideas to continuity and one-sided limits. I'll see you in the next lesson.